Hello class, welcome to our calculus course. This is Calculus Volume 1 and we will begin with a refresher on prerequisite topics from Chapter 1. And let's start off with functions and graphs. So we have function notation, we have definition of functions, domain and range, those kind of things that we were introduced to in our algebra. And so we'll take a quick look at them. And under function notations, if you recall, we used f of x, right, to say f, you read it as f of x, right? So it's a function of x. If it is a function of some other variable, let's say t, then you can have f of t or s of t and so on, right? So we used this notation as a way to upgrade our equations into functions. So what are functions then? The definition says for every input there's exactly one output. And so we want to understand that by looking at how functions are mapped through domain and range. So we want to recall that you cannot have your x values repeating for it to be a function, right? So you can't have two x's going to the same y. You can have one x going to two different y's. That is permitted. And so we want to remember those details in the definition of functions. And domain and range, domain is the collection of all x values that keep the function defined, and range refers to all the y values that keep the function defined. So let's take a look at some examples here. Okay, so we have y equals x squared. Okay, you know that this is the equation of a parabola. It's a quadratic equation. If I were to write this as f of x equals x squared, then I'm using the function notation, and you know that that is a function. If I just say y equals x squared, it appears as an equation, and we know from our understanding of functions and different families of functions that y equals x squared, although it's presented as an equation, you know it's a function, meaning if you don't have the f of x notation to denote it, we still know that it's a function. So you want to keep those things clear in mind. Okay, so if you recall, the graph would look like this. Right? That's y equals x squared. So when we talk about the domain and the range, you're looking for all the x values that keeps this function defined. All the y values that keeps this function defined would be the range. So if you look at a graph and try to understand all the x values, you're looking at your graph from leftmost end to the rightmost end. How does your graph stretch from end to end? So the leftmost end, as you can see, it's pointing to, there's an arrowhead, which means that it's going endlessly. That means this left end of the graph goes on, right? As x approaches negative infinity, this graph just goes on towards infinity. And on the right end of the graph, there also you see the arrowhead, which says that this graph goes indefinitely on the right. So as x approaches positive infinity, you have the graph approaching positive infinity as well. So you know that your domain, in this case, it's uninterrupted. You don't see any break in your graph, the red graph. When I say graph, I don't mean the grid. Okay, I mean the function itself, the graph. And so that goes all the way from negative infinity to positive infinity, left end to the rightmost end. So I'll just say left to right. Okay, and as you know, infinity and negative infinity, these are not numbers. They indicate a state towards which the graph is approaching. So we cannot include them in our graph, and so remember to use parentheses for them always. And then range. For range, you want to look at your graph this time, but against the y-axis. So if it's a y-axis, you know how it goes. It goes top down, right? So you're going to look at the bottommost value against the y-axis to the topmost value against the y-axis for the red graph. So the bottommost value against the y-axis is the 0, right? Your graph doesn't go below 0. And on the y-axis, it goes all the way up because of the arrowhead, you know it's going to go all the way to infinity. And we know that there is no break or open circle or any kind of disruption in the graph. It's a smooth, continuous graph, and therefore you know that 0, that point, your graph passes through it, which means it's included. And therefore you come back here and say, well, my range is the bottommost, which is 0 included, all the way to infinity on the top. So this is 0 here, and this goes all the way to infinity, right? This one is negative infinity at the bottom, but there is no graph happening below the x-axis. So you go from 0 all the way to infinity. Remember to put a bracket for 0 to include it, and a parenthesis at infinity to say that that's not included. Okay, so B to T, bottommost to the topmost part of your graph. Okay. Now, so you're going to now look. We're going to look at some examples where I will give you some functions, and you'll have to figure out their domain and the range. Okay. So at this point, you could pause the video and do it by yourself, and then come back and see if our answers match. Okay. Now, the other exercise I want you to also remember to do here is, it's so much easier if you are able to look at these things visually. Meaning, if you can remember how the graph looks, it really makes it so much easier to determine the domain and the range. So you know this is a rational function, right? And so a rational function would, in this case, this would be like this, right? So remember that. And therefore, the domain here would be, there will be a break at 0, okay? Because your rational function has branches, and for this particular function, it branches off on the first quadrant and the third quadrant. So there is a break at 0. So you indicate that break at 0 because it's continuous everywhere else except at 0. So if you're removing just the 0, and it's not included, so you have to have parentheses at 0, of course. And that's how you write the domain, because of the break. Okay. And this is a four-way situation, so you have the break also for the range, and there also we have a break at 0. Okay. Think about this next example, y equals square root of x. This is a square root function. So think of the graph as going like this, right? Only the first quadrant. So, and if you are having little difficulty, or it's a little rusty for you, this is the time for you to, actually explore and figure out from your graphing calculator, punch these functions and see how your graphing calculator projects the graphs for these, and that way you can quickly try to refresh your memory on these. Okay, now because it is a square root function algebraically accepts 0 under the radical sign, but it cannot accept negative values. So we have no problem in starting our domain at 0 included, and it goes all the way to infinity. It accepts all positive values. Same holds true for y, for the range as well. So this is also going to go from 0 to infinity, because it's all happening in the first quadrant, and we start at 0, 0, so this works fine. And then we have y equals square root of 4 minus x. Think about this. It is again the square root function, but it's not starting at 0. It's 4 minus x. So you can again put it in your graphing calculator to see how the graph runs. And you will also begin to see that the graph actually will accept all negative values, because you have 4 minus x. So if x is negative, that negative value, when you plug in a value for x, which is negative, that negative combines with this negative, thus making it a positive value, right? So we can do that all the way up to 4, because once you reach 4, 4 minus 4 is 0, that is good. But once you go past 4, if you take the value, let's say 5, 4 minus 5 is negative 1, square root of negative 1 is undefined. And therefore, we can see that from the graph. Okay, you can also look at it algebraically by understanding that your radicand, the expression under the radical symbol, the radicand must be greater than or equal to 0. Right? It can be 0, but it can't be negative. So it has to be 0 or other positive values. So you can use this to kind of solve for x. Okay, so 4 is greater than or equal to x when you solve for it, which is the same as saying x is less than or equal to 4. That means your x values here will accept all values that are 4 or less. That means all the way from, so rewrite this inequality in interval notation. So you go from negative infinity all the way to 4. There's an equals bar there for 4. That means you can have the 4 included. So this algebraic approach helps you to get your domain. Okay, if you're not looking at the graph, you can do it algebraically like this to get your domain, and we know that this is going to be negative infinity to 4 for the domain. And for the range is the corresponding y values, right? So again, look at your graph to get the corresponding y values, and then you will see that this has to be, it's square root of 4 minus x. For these x's, your corresponding y's will have to be 0 or positive, right? Because you can't get a negative answer coming out of a square root. So unless there was a negative outside the square root. Here that's not the case. Therefore your y values will have to be 0 and positive. So your range will be 0 to infinity, 0 included. All right? So let me clear this. Try for this one. Use your calculator and see what your domain and range are. You will see that this is going from negative 1 to 1, and this is 0 to 1. Next, let's talk about graphs of functions. Now we defined that for a function, for an equation to be upgraded into a function, every input must have exactly one output. So you can't have your x's repeating. Now on a graph, how do we determine that x's do not repeat? If you're looking at a function, or if you're looking at a table of values, x and y values, you can easily see that x's are repeating or not. But how do we determine that from a function that's presented as a graph? For that, we of course use the vertical line method. Remember, vertical line method helps us to determine if if a graph is a function or not. So vertical line method, or test I should say, vertical line test tests if when you draw vertical lines throughout the graph, okay, vertical lines throughout the graph, then you want to make sure that your vertical line crosses the graph at most once. So no more than one time can it cross for the test to pass. So if I had a function that looked like, like this, okay, so then I have to drop vertical lines throughout the graph everywhere you're performing this test, and you see that it hits the graph only once. That means the test passed. That in turn means that this brown graph is a function. Okay, so you don't really need to know even the equation of it. You can just perform this test and determine that. Now if I had let's say a circle as my graph, now perform the vertical line test, and you see that it hits it at more than one place, right? The vertical lines that you're testing. So even if it happens in one place, we've lost it. Therefore we know, because that simply means that for this x value, it is that x value has the same x has two different y values. That's what this means, right? So let's say this was 1. So this could be like 1, 1, and this could be like 1, -1. So your x's are repeating, and that's why it cannot be a function. And that repeating x's is caught by this vertical line test. So you perform vertical line test on graphs. If it is and then we also have other properties. We call them transformations, like translations, meaning shifting of graphs. We have reflection of graphs, up down reflection, left right reflection. We also have shrinking and stretching of graphs. So I'll just simply say transformation of graphs. So please go ahead and refresh your memory on this. You can go to our ebook and look up chapter 1, because they go over all these things as a quick refresher. Okay. And when we want to express a graph, not visually as a graph on a grid, but we can also express the graph as a table, right? The t table, xy table. So you can have the x values and the y values. We cannot exhaust all the values because we just saw that the domain for some of them is negative infinity all the way to infinity, right? In fact, for that matter, if you look at this domain here, negative 1 to 1, even that has infinite number of values in between them, right? And therefore, we really cannot exhaust all the x values and y values in a table. We will just choose enough values to help us to trace out the shape. So a table would not be completely exhaustive, but it definitely gives you the values more explicitly. Okay. And sometimes when a function, when a given equation is not a function, or when your graph fails the vertical line test, we should be able to use restrictions on the graph, limit your domain. So restrict your domain and to make it a function. Okay. So remember that those things will also be considered. So restrict the domain to make it a function. And to backtrack a little bit on the table part, you can use the table method to graph functions, right? So we can express a graph in a tabular form by giving out the x and the y values. But if you want to graph a given function, so let's say you wanted to do the y equals x squared function, okay? So if you wanted to graph it, you need to have the x and the y column like this. And you'll have to supply, generate your own x values, because we know that for y equals x squared, if you come back here, the domain is all x values. So we have no restrictions. So you can choose any x value. But because we expect this to be a parabola because of degree 2, it's going to be a parabola. And we know that because the coefficient of the leading term is positive, it's going to be open. It's going to open upwards. So we know these clues from pre-calculus. We learned about those clues. You can supply your own x values. So for that, I'm going to just give in -2, -1, 0, 1, and 2. Please remember, you're in calculus, so you don't always go for only the positive values. You'll have to spread your graph, negative side, positive side, provided your domain accepts them. And for us, we had no restriction on the domain, so you have to spread your graph, on the left and the right of 0 in this case. So now plug in -2 in the place of x to get your y value. It's going to be 4, -1, so now we've got your x and the y columns done, which means those are your coordinate pairs. You can go ahead and plot them, right? -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. So if you go to your graphing grid, then you have 0, 0. Then you'll have the -2, so that's -1, -2, 1 and 2, 1, 2, 3. Sorry, I'm squeezing it here. 4, negative. So if you have that, then you're basically plotting it, right? -2, 4, then -1, 1, 0, 0, 1, 1, and 2, 4. You know that it's going to be a smooth curve. And you got your graph. So that is how you use the table to graph a function, and vice versa, right? A function, a graph on the grid can be written as a table, and a table can be drawn. A table can be computed to help us to do the graph. So I'll remove that. So what we see is that they are all interdependent in that sense, and they can be represented in different forms. So a function can be represented as an equation, can be represented as a graph, can be represented as a table, can also be represented verbally, a verbal description in word problems, right, where you can see that. So here are some examples for you to go ahead and graph and practice. So if we say graph y equals x squared on -2 to 2, then you know that you're trying to graph this only between -2 and 2, which is your domain, right? So this is your domain. So you can't choose any x you want. So because you're trying to graph this one, you're going to get your t table, right? It looks like a t, isn't it? So this is your t table, and you go ahead and plug in values between -2 and 2. So -1, 0, 1, and 2, what we just did, right? If I gave you the domain, a restricted domain, this is restriction, right, on the domain. So if I gave you -1 to 2, then you cannot use the -2. You have to go from -1 all the way to 2, and so on. We like to use whole numbers because it's just so much easier to compute. But remember that between -2 and 2, you have infinite possibilities, right? Because if you look at it on the number line, -2 and 2, your x values are all these values, which is infinite possibility. What is the number right before 2? What's the number right before 2? If you're thinking 1, you are absolutely wrong. Because what about 1.9? Right, 1.9, because it's on the number line. We're not jumping by whole numbers. You cannot just skip all the numbers in between 1 and 2. So if I'm talking about what's the number right after or right before 2, you're thinking 1.9. I would say 1.99. You can counter it by saying 1.999, and I can go with one more extra 9 there. So you can go on like that, and you have no end to the number of 9s you can place right after that 1 point, isn't it? So you see that there are infinite possibilities. So you really cannot exhaust all these values on your graph, but you must understand that there are infinite possibilities. So don't, just because our table takes only whole numbers, do not assume that only those can be there. These are all continuous values. Okay. So try these out. I know that you did use your graphing calculator for this one previously, but here I want you to graph it yourself by supplying x values based on your domain, because your domain here would be -1 to 1. Make sure you generate values between -1 and 1 to get your corresponding y values. Okay. And try to graph this one, -√1 minus x squared. See what happens there. Okay. Try to graph x squared plus y squared equals 1. How would you graph x squared plus y squared equals 1? Okay, you can rewrite this equation in terms of y, and try to get your table based on that. That way you can plug in for x values and get your corresponding y values. If you recall what this function format is, then it makes it a whole lot easier. A hint for you here. This is actually the equation of a circle. So go back and refresh your memory on that lesson. Conics. So this is the equation of a circle with center 0, 0 and radius 1. If you remember that format for the equation of a circle, your life is so much easier, because all you have to do is draw a circle with center 0, 0 and radius 1, and that would look like this, right? So if your center, so your coordinates basically would be 0, 0, radius is 1, so you go all the way there 1, and then radius here is 1, here is -1. Remember, radius is always positive, but you're graphing this on a grid here, and therefore you get all these points, right? And then all you have to do is draw your circle through it. Okay, now mine is going to look really terrible because not bad. Okay. So this is how you graph your circles, and so it makes it a lot easier because you're trying to utilize the idea of the format of equation of a circle. That is why we really like these forms or formats. Okay. The equation of a line, the general form, y equals mx plus b is the slope-intercept form. We also have y minus y1 equals m times x minus x1, which is the point slope form or slope point form. So these are all formats which, if you remember, they work like templates, and it helps you to recall what they stand for, and that these two are equations of a line. Likewise, ax plus by equals c is the standard equation of a line. If you have ax squared plus bx plus c equals 0, this is the quadratic equation. Or if you set it equal to y, then you can plug in for x's and get your y's and so on. So we have, and we just saw that x squared plus y squared equals r squared. would be the equation of a circle with radius r and center 0, 0, because those are the two things you need for a circle. You need the center and the radius. And go also for the format where if you had a different center, if it was not at the origin, if it was a different point as the center, then you'll have the h and the k involved in this. Then you have vertex form for quadratic equations and so on. So we have plenty of these forms, which I recommend that you recall, go back and refresh your memory on that. Okay. So try graphing all these ones and you'll get an idea of how to utilize your XY table to graph them, because that is the traditional way, the standard way to graph any function, any given function. The T table is the way to go. Now if you have the knowledge of these formats, then you can skip the T table and use the formats to get to your graph quickly. Alright, we have something called piecewise function. As the name says, these functions appear in pieces. So one of the most popular examples is absolute value function, which is actually a, the function actually looks like a V, isn't it? But it's actually two pieces, 1 and 2. These are two lines that are connected at 0, right? So because it's got two pieces, the piecewise function for this is actually, we write it as absolute value of x, right? This is actually a collection of two pieces, where one piece is y equals x function, which is when x is positive, and y equals negative x, and this is when x is negative. Okay, so you know that these are called, of course, pieces. This is a function, fn for function. Okay, function piece, and this is another function piece. When I say function piece, that means you read it like y equals x. You read this like y equals negative x. And they come with your own domain. So this y equals x has this restricted domain. So you're going to graph that only for that domain. Because y equals x actually would be like this, all the way down here, right? But then because you're only choosing x to be positive, this portion would go off and you just have the right, the piece in the first quadrant. Likewise, y equals negative x is this entire piece that's going between second and the fourth quadrant. But once again, because your domain is restricted for all x's less than 0, you only have the negative arm of your x-axis that will carry that piece. And so your piece actually lies only in the second quadrant. So I have to kind of renumber this correctly. So this will be the first piece for the first function piece that's defined here. And this will be the second function piece. Okay. Then we have increasing and decreasing functions. Remember again what the rules indicate. We always read our graph from left to right. So for increasing, it implies this two lines with an arrow means implies. Shortcut for implies that if x1 is less than x2, that implies the function f of x1 is also less than f of x2. Okay, that is increasing. As x increases, y also increases. Decreasing function implies that if x1 is less than x2, then f of x1 is greater than f of x2. That means as x increases, y decreases, because f of x is your y, right? So and basically your f of x is your y, which in turn is your graph itself, right? The graph on the, not the grid, but the graph that you draw on the grid. So as your x increases, if your y also increases, meaning if your graph rises, then you know that we're talking about increasing function. So just to put it in English, it means that it rises. And if x increases and y decreases correspondingly, it means the graph falls. So you read your graph always from left to right. And when you read your graph from left to right, if your graph increases, meaning if it rises, then you know it's an increasing function. And when you read your graph from left to right, and if your function decreases, or if it falls, then you know it is a decreasing function. And we know we have to read it from left to right because that's how your numbers increase on the number line, right? So you go from negative values all the way to positive values on the right. So your numbers increase from left to right. So that is why we always read our numbers from left to right, right? So this is trivial, but I want you to understand that if it's say, on the if I zoom into the number line where 2 and 3 are, okay, you always say 2 to 3. Your interval would be from say 2 to 3. You will never say 3 to 2. You can't say I didn't realize that, I didn't, you know what I meant. No, if you write 3 to 2, I will not know what you meant. I will just understand that you got it wrong. You didn't understand the way, because remember, math speaks through numbers and symbols. So if you misused your symbol, then it misunderstands the meaning that you were trying to convey. So we want to make sure that we understand correctly what you mean by using the correct symbols. It's also similar to saying I'll meet you between 2 p.m. and 3 p.m. That makes sense. If you say I'll meet you between 3 p.m. and 2 p.m., it totally is different, because what you mean then, again, is very, very difficult but to interpret. But it could mean actually that it's 3 p.m. in the evening, all the way through the night, and all the way the next day afternoon up to 2 p.m. So if you say 3 p.m. to 2 p.m., that's what it means. Nobody would understand that you meant 1 hour. It would mean that it was 11 hours. So you really want to make sure that we interpret and also express our answers correctly. Okay. Then we have even and odd function. And even and odd function basically refers to the symmetry. Okay, so so graphically speaking, we would say symmetry. Algebraically speaking, we have a specific rule. The rule is, if I replaced all the x's with a negative x in my function, the function would remain unchanged. Okay, that's what it means. This is algebraically, this is how you test for symmetry, for evenness. But graphically, it is symmetry about the y-axis. Okay, so it is, if you folded your graph along the y-axis, the graphs should touch each other. They will coincide because they were symmetric. The left and the right sides of the graph, or rather halves of the graph, will be the same. That's symmetry about the y-axis. So you can think of your y equals x squared, right? Your quadratic to be an example of an even function. If it's an odd function, the rule says, if you replaced your x's with a negative x, it will be the negative of the function. The result would be a negative of the function. This refers to symmetry about the origin. Okay, please don't think it's about the x-axis. It's symmetry about the origin, so across the origin. So it's like folding your paper twice, one first along the y-axis and then along the x-axis, and then the graphs will touch. Okay. So a quick example for this, for the symmetry about the y-axis would be this, right? So the left half and the right half are symmetric. For symmetry about the origin, then it's like your first quadrant and your third quadrant, right? So then if you fold along the y-axis and then fold one more time below on the x-axis, you will see that they will coincide. So that is the idea of origin. Another way to remember is use the alliteration O and O for odd and origin. It's not the x-axis, it's the origin. Okay. And go through the functions, the examples given in the ebook. Remember, these video lectures are overviews. They are not going to be completely exhaustive. These are meant to explain and teach you the concept, not necessarily mimic your homework examples, because homework examples are the place where you practice and apply these concepts. So do not expect me to teach your homework problems here. I'm teaching the concept. So I want you to really open your ebook and look at additional examples. You cannot just only watch the video lectures and somehow think that that will satisfy your understanding. It will not. Okay, so please go ahead and check your ebook, your OpenStax book, for further examples on this. All right, linear functions. We just saw y equals mx plus b. ax plus by equals c. And this again stands for the slope-intercept form. It is very, very clear, right, that your m is the slope and this is your intercept. We have two intercepts. You have the x-intercept and the y-intercept. This is always your y-intercept. And this would be the standard form, where your x and y are on one side of the equation and the constant is on the other side. So a, b, and c stand for real numbers. Y minus y1 equals m times x minus x1. This is called the slope point form, or point slope form, however you'd like to call it. And this again is a template where m is the notation for slope, right? So you know that that's the slope. And this x1 and y1 will be the point. So there is a slope and a point. So if you have the slope and a point given to you, you can plug them in this template in the right position so that you get an equation containing x and y, which becomes the linear equation. And you know, if it's linear, you see the word line hidden in it. So this will always produce a line when you draw the graph. And these are a family of functions. They behave this way. They will be in one of these formats, and if they belong to these formats, you know it belongs to the linear family. And linear family is a family of functions that will always produce a straight line. That straight line could be horizontal, could be vertical, or could be slanted, but it's a straight line. So don't just say straight line, because we never draw crooked lines. Okay, so linear function is always going to produce a line, a straight line. Okay, and the line could be in one of the three ways. It could be vertical, horizontal, or slanted. The only catch is that if it's a vertical line, we don't call it a linear function, because it fails the vertical line test function itself completely, right? So we will just call it a line, not a function, not a linear function. So technically speaking, when we talk about linear functions, we're talking about horizontal lines and slanted lines. We will not include the vertical line in the function because it fails to be a function. All right, now we can make a connection between the slope and the increasing, decreasing behavior of the line. So if your slope is positive, you know that the line increases, right? That means your graph would be like this. I'm talking about linear functions, so I'm just talking about a line, right? So this means if your slope is negative, so which means if you can just look at your equation, if you can determine the slope from it, just by looking at the number, because slope is a number, right? So just by looking at the numerical value of it, is it positive or negative, you can determine how the line will behave, and that is really powerful. That means the graph falls, right? So it's a decreasing function. And if your slope is 0, what does it mean? The slope is the slantness of a line. So if the slope is 0, it implies that the line is going to be horizontal because there was no lift off. It just remained flat. Okay. So in math, we don't use the word flat. We would call it horizontal. Okay. So if I were to say how the line will be a constant. And if your slope is determined to be undefined, that is because the line was vertical, because a vertical line is not a function, therefore the slope is not defined. Okay. And the format for a horizontal line is that y equals some number. You won't see the x there. Okay, that means it is a horizontal line. And if it's x equals some number, so if it's x equals 3, then it is a vertical line passing through 3 on the x-axis. If it's y equals -7, then it is a horizontal line passing through the y-axis at -7. Horizontal line is a function, vertical line is not a function. Then think of, go back and refresh on proportionality, where x and y will be variables and k will be the constant of proportionality. I'm not trying to teach all these things here, it's a review. So go back and refresh yourself on that. You can also look at watch Khan Academy videos. They are free to watch, and they go over these things in great detail, and those videos are phenomenal. So check out Khan Academy. So if I say y is directly proportional to x, that implies you set up your equation as y equals kx, where k is the constant of proportionality. That gives us the rate in which the two variables vary. Okay, and if y is inversely proportional, now that is a description, right? That is it's a verbal description. But if you were to convert it to an equation, it's going to be y equals k over x, where k is the constant of proportionality. Because it's inversely proportional, one variable is in the bottom, the other one is on the top, on the other side, right? So direct proportionality just means if when x increases, y also increases. When x decreases, y also decreases. But when it's an inverse proportionality, then when x increases, y decreases, or when y increases, x decreases, and so on. So that's their relation there. Okay, then let's talk about power functions. Where n is a constant. Okay, power function is when the exponent has a power. The exponent is this spot, right? So this one is a constant. So this is your power. So you change your n. X power 0 we know is 1. X power 1 is x. X power 2 is x squared. X power 3 x cubed, and so on. We like to use usually, and you can have fractions, you can have negative numbers, and so on, right? So all that is possible. So your n is a constant. And so this is different from exponential functions. Exponential functions the other way around. Your x will be sitting in the power. In this case, your n is sitting in the power, x is in the base, so we're good here. So then we have, you can say, when n is 1, your f of x is x itself. And your graph would be f of x equals x, right? When n equals 2, your f of x is x squared, because your n is now 2, and you know that your graph for that would be very familiar. F of x equals x squared. Likewise, when n is 3, you get x cubed, right? So I'll just try to graph the graph when n is 3. X cubed is the chair-shaped graph. I can just say x cubed here. And when it is x power 4, it looks like your x squared, but it's a little flatter when it passes through 0. So f of x equals x power 4. X power 5 would look very much like x cubed, but it's going to get flatter. And we've observed this phenomenon in pre-calculus. We talked about multiplicity and all that, right? So again, go ahead and refresh that. So this will be f of x equals x power 5. It's just grown flatter at 0. Alright, what happens when n is negative 1? This means this is f of x equals x power negative 1, you know, from your law of exponents, that you will switch it to 1 over x. And you know 1 over x is instantly a rational function, and so you have the graph branching off. Okay, because your x, when x takes the value 0, the 1 over x becomes 1 over 0, which is undefined. That is why you can't have the graph passing through 0. Nothing happens at 0. They kind of deflect at 0 because of that condition, right? So that is your f of x equals 1 over x. This is still a function, because in its domain it is defined. It is a function, right? In its domain. So the domain is that, just to put it simply, it's all x values except 0, and the range is all y values except 0. This is not the way to write your domain. You always write it as the interval, but I'm just doing it shorthand because we already discussed the domain and the range before. Okay, what happens when n is 2? Negative 2. So that's f of x equals x power negative 2, which is 1 over x squared. So go ahead and look at your graphing calculator. You'll see that when it's x squared, it actually has both the branches going upward here. When say n takes a fractional value, let's say n is a half, that means f of x is equal to x power half. And remember how you will convert a rational exponent into a radical. Rational to radical and radical to rational, they're related. So that will be square root of x. Your f of x is basically a square root of x, because x power half is square root of x. The 1 is the power, and that will be the 2 in the bottom is your root. Let me quickly point to that. Okay. So in your exponent, you see that this would be starting at 0. It will go in the first quadrant, and we saw this also again previously in our domain and range. So you got that. You'll see a lot of these in calculus, so that's why I'm spending a little more time with the different n values. Okay, so if it is 1 over 3, f of x is x power 1 over 3, and you know, if you were to write it in a radical notation, it's radical with the cube root of x, and then the graph for that will be if you look at this, this is actually the flip of your y x cubed, y equals x cubed, right? X cubed is this chair-shaped graph. It's a flip of that because that is how these two are connected. The power and the root are inverses of each other. So f of x equals cube root of x, or x power 1/3. Okay, now what about n being 3 over 2? That's x power 3 over 2. Remember again, the power is, the top is the power and the bottom is the root. So f of x would be square root, right? And you don't never put the 2 for the square root, only past 2 you will put the other ones. So this is going to be square root of x cubed. Okay. So if you were to look at the graph for it, it's going to look a little strange. It'll look, somewhat familiar, somewhat strange. So it should look something like this. Y equals x power 3 over 2. Remember again, it's square root and it's x cubed. So square root cannot take negative values, so you have that restriction, but x cubed is happening inside the radicand, so your graph looks a little different there. So it's like just the cubic functions as if it's part of it, or something like that. All right, what happens if it's 2 over 3, n equals 2 over 3? This is going to look a little more complicated because this becomes algebraic at this point. 2 over 3. And so it's cube root because that's the bottom. So cube root of x squared. Cube root of x squared, and that also looks a little unusual. We've not seen this. It's as if it's kind of sprinting, So that's going to be y equals x power 2 over 3. And so on. So I want you to go and explore these things, with more other functions, and try to learn how your calculator works as well. Then we have polynomials. This is the general expression for it. We express, or the notation we use for functions is f of x. And polynomials are also functions, but the preferred notation for that would be p of x, polynomial in x. So an x power n. Polynomials means many terms. Poly is many, nomial terms. So it's a sum of many terms. a1x plus a0. This is how it would expand, right? And in polynomials, the degree is 1. Remember, degree is the, well, if you had multiple variables in one term, then you add the powers for those variables to get your degree. But in a polynomial like this, we only have one variable. X is the only variable. So it is a lot easier to just look at their power to determine the degree. So if your n, if the degree is 1, then you know it is a linear function. The polynomial becomes a linear function. If the degree is 2, the polynomial produces a quadratic, which is always a parabola. If the degree is 3, it produces a cubic function, and so on. Okay. So polynomial is kind of a very general version of all these functions. When you keep changing the degree, you produce specific functions, right? Okay. Then let's talk about rational functions. Just to come back here and kind of told you what polynomial stands for, right? So poly means many and norm means terms. Likewise, if you come to rational, the word contained in rational is ratio. Ratio means fraction, right? Some kind of a fraction. So let that be your clue to know that we are talking about a fraction. In particular, it's a fraction of polynomials. So if it's a rational, it's a polynomial over a polynomial. That's how the setup is. Okay. So your function, a rational function, f of x, would be actually a ratio of two polynomials. So remember that. And because of the fact that you now have an x in the denominator, x is a variable, so it can vary and take any value. And we have to be careful to figure out for what value of x will the denominator become 0. Because where it becomes 0, the function becomes undefined, and there will be a break in the graph, right? Wherever it's undefined, there will be a break. And therefore, we want to pay that extra attention here, okay? Provided the q of x is not equal to 0 for a particular x. So if you found a particular x, you have to exclude it from your domain and get your graph, okay? So, you can have, crazy looking functions here. Like for instance, let's say if your function was 2x squared minus 3 over 7x plus 4. When you're given something like this, you know it is rational because your numerator is a polynomial and the denominator is also a polynomial, and of course it's set up as a fraction of two polynomials. And therefore, you can understand that this is a rational function. You could have something like this: 5x squared plus 8x minus 3 over 3x squared plus 2. So you want to always make sure where the function becomes undefined. Like for instance, in this case, when x takes the value, set the denominator to 0. So let me just show that maybe. Because that's when we know where it becomes 0. So set it to 0. And then if you solve for x, you get negative 4 over 7. That means in this function, this is where your function becomes undefined. So there will be a break at this point. You can anticipate a break in this point on the graph. Okay, so the graph will branch off on either sides of this negative 4 over 7 on your grid. On the other hand, here, if you set this to 0, right, you get x squared equals negative 2 over 3. X squared is negative 2 over 3. So if you do x, it's plus or minus square root of negative 2 over 3. Right there, you have all this complication there, right? First of all, you get a square root with a negative radicand, then you have a plus or minus. So technically what we're saying is, we cannot find an x that will make the denominator 0, isn't it? Because even if you found a negative value, say for x, when you plug it in, it's going to get squared, and so it's not going to produce a 0. If you have a A positive x, when you square it, it does not produce a 0. If you plug in x as 0 itself, you still get a positive 2. So there is no x value in the real number system that will make this undefined because of the denominator. So this will be a rational function without any breaks, without any branches. Okay. So you always want to explore the limitations and the domain of your rational functions. Algebraic functions. So these are functions that come out of a combination of algebraic expressions. So I can have something like this. We know separately what x power 1 over 3 will look, and we know x minus 4. These are two separate functions, we know. But algebraic functions are a combination of these functions. You're multiplying these two known functions, so that actually will produce something very different. Okay, so the graph for this could look something like, I don't know, something like that. Okay, and then you have y equals 3 over 4 x squared minus 1 power 2 over 3. The function looks complicated, but the graph looks actually cute. Okay, so it looks like this, something like this, okay, and so on. So you can have a combination like this. Okay. Then we have trigonometric functions. And we have 6 trig functions, right? Oops. And this was a separate course that you took. Okay, all the other ones we've seen in algebra, but this was a separate course. You did this in trigonometry, or and you've seen it again in pre-calculus. So this must be super familiar to you. Cosine, tan, cosecant, secant, and cotangent, and you know how they're related, right? Tan is the ratio of sine and cosine. Tan is sine over cosine. Cosecant, of course, I just mentioned the name of the functions. You never write a sine by itself. It's always a sine theta, a sine x, a sine alpha. It always comes with its angle, right? So I hope you understand that I mean that. Cosecant is a reciprocal function of sine. So 1 over sine is basically cosecant. Secant is the reciprocal of cosine, and cotangent the reciprocal of tan. And ultimately speaking, these are your parent functions. Okay, and even there, sine, if you adjust it, it can coincide with cosine, and vice versa. Cosine, when adjusted, would overlap with sine. So technically, these are the two functions, and these are two wave patterns, right? We've seen. And they have their properties, and based on which the other functions are derived. So if it's a sine function, we know a traditional sine function. I'm just going to graph one period. I'm going to extend that a little bit. This is y equals sine x, or sine theta. It just depends. I'm just using x and y because we're familiar with that, right? And if you're using a cosine function, then one period, when I want to graph one period, it's going to look like this. Looks more like a V, right? But then you know that this is just one period, but if you were to extend this, right, you can see the wave pattern. So the wave pattern, they both are wave patterns, but if you took one and overlapped it with the other, by shifting it appropriately, you will get the two functions behaving the same way, right? And so in trig function, we've seen the importance of, all the important angles, isn't it? If you draw the spokes through these, okay, the axes and then the ones across, it looks like this. And so you'll have your angles, of course, in degrees and radians, right? So 0, 2 pi also comes here. And then you have Now let's just look at the dark green ones. So that's 0, pi over 2, pi, 3 pi over 2, back to 2 pi. And then if you look at the 45-degree mark, the blue ones, right, it's pi over 4. So it's basically pi over 4. The green, the x-axis, the y-axis would be 2 pi over 4, 3 pi over 4. This would be 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Because when you reduce all those ones that coincide with the axes, then they all reduce to pi over 2 pi, 3 pi over 2, and 2 pi. Because 4 pi over pi in the pi area would reduce to a pi. 8 pi, because after 7 pi over 4, it's 8 pi over 4, which reduces to a 2 pi. So you got that. You could also do it in terms of pi over 12 to get your, let me find another color. Okay. So to get all these, the cyan green, the light green ones, so we can have, we can start with pi over, if you did pi over 12, you have to kind of break it, let me just show it to you here. You need to break it further like this, okay? And then you could do pi over 12, 2 pi over 12, and so on. But you could also just simply start with pi over 6, okay? 0, pi over 6, so you're jumping by pi over 6. So 2 pi over 6, so you're going to skip the blue ones, and this would be 2 pi over 6, which is basically pi over 3. You have to go back and reduce. 2 pi over 6, 3 pi over 6, 4 pi over 6, skip the blue, 5 pi over 6, 6 pi over 6. You know you did it right when you land in pi as 6 pi over 6, right? This is 7 pi over 6, skip this, 8 pi over 6, skip this, I'm sorry, not skip, 8 pi over 6, 9 pi over 6, this will be 10 pi over 6, skip this, skip only the blues, 10 pi, 11 pi over 6, and you're back to 12 pi over 6, which is 2 pi. Now go ahead and reduce all these things. Pi over 3, 2 pi over 3, this would be 4 pi over 3, 5 pi over 3, and so on. And then of course you remember your coordinates, right? Your coordinates would be, it's a bad color, it doesn't project well, so 0, 0, I'm sorry, 0, 0, 0. There's no 0, 0 there. This is it's a unit circle, right? So the radius is 1, so 1 comma 0, sorry about that. So at 0 I meant it should be 1 comma 0, okay? And then these are the points on the circle. Right? So I'll just do it for the first quadrant, and then just to help you recall, right? So there's again a trick to help us remember this. By the way, this would be 0, 1 here, the 90-degree mark. The trick would be to get your coordinates. There is actually a derivation for this. I'm just, because you've learned about that, I'm just teaching you the trick to help remember this. Okay? So all of them will have a division 2 for these 3 points in between. So what we're saying is do 1, 2, 3 on the numerator, and then go in reverse. 1, 2, 3. Take the square root on the top. Square root of 1 is 1. The others you have to leave it. So you get your coordinates. Use the idea of ASTC, right? All students take calculus, so that you know which quadrant carries what signs and so on for the for your sine, cosine, tangent, cotangent, and their reciprocal functions. So that is a quick gist about your unit circle. And you know that you have the triangle to do the SOHCAHTOA, right? Opposite, adjacent, hypotenuse. So I'll just say so as S-O-H, SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay? So recall all those things. Then we have logarithmic and exponential functions, but because we are following late transcendental pattern here in this calculus course at Merced College, we will be looking at the logarithmic functions and exponential functions in calculus 2, especially derivatives and integrals related to those. Okay? This was just a gist. Of course, you know, I'm not trying to teach you all of algebra, but I hope that this gave you an idea of all the things you have to go back and recall, and it's quite a lot. Okay, so whichever one you feel you're rusty, you'll have to go back and recall. In trig especially, we have all those functions that for which you should recall the graphs, then the periods of each function, the trig identities, you know, that's a big deal. Well, of course, you can use the sheets to help you with that. Then we have, you know, sinusoidal functions and, you know, special inequalities and things like that that may appear there. So I want you to pay attention to those things, because when we begin to graph, we want to really be very clear about this. So when I say sinusoidal functions, I basically mean, you know, formulas that involve sine or cosine. So, you know, we've seen this, right? Cosine 2 pi over b x minus c plus d. A stands for the amplitude, b helps you find the period, c over b, that helps you to with the phase shift, and d is your midline, a vertical shift. So you really want to recall all those things, because it should be in your fingertips for your calculus. More importantly, it is essential that you are really, really good with the graphs. Okay, expose yourself to multiple functions and check out their graphs, see how they appear, know their families, know the properties that go with each of these families, and that's going to really, really help you, especially in calculus and your journey in calculus. Okay, I hope you got a good shake of review topics. This will propel you to go further and review them. I will see you in Calculus Chapter 2, where we actually begin with the calculus lessons. Thank you, class.